Welcome back. In today's class, we will continue the concept of self and mutual inductances. In the last class, we have seen how to determine the self-inductance of a long solenoid, and we have determined and we have derived these expressions, right? One was n d phi by di. If phi was constant, then we use it to employ n phi by I, and if we do have the length and area of cross section of a solenoid, we try to employ this particular equation for determining the length of a solenoid, right? So now in today's class we will see how to determine the self-inductance of a toroid and also the mutual inductance of a toroid. Now, first of all, let's take what you mean by a toroid. A toroid is just like here a long solenoid. Normally solenoid will be in this fashion, whereas if you bend this one in this circular fashion, then it is called as a toroid. So shown on the figure is a toroid. Now in this case, if you carefully see, it is just like a circle. Now this is your medium and the coil is wound on it, and you are allowing a current of I to pass through it. Now if you carefully observe, you can see now that there are two radius. One is a radius of the inner side and the radius of the outer side. So how to determine the length of this particular one? Because we do have this formula, mu is equal to, L is equal to mu n square AY L, right? So L here indicates the length of the solenoid. So in this case, how to determine the length of the solenoid? This is a big question. So for that one, we will employ this particular equation. We will take the mean radius, which is equal to Ri plus Re by 2. As you might have seen, this is a solenoid, right? This is the inner radius, this is the external radius. So I'll take the average of these two as a mean radius. Now the length of the magnetic path is a circumference, right? So for the circumference of a circle, you know that it is 2 pi r, right? So I'll take the mean radius as the radius of this path. So I'll get 2 pi rm. This is the length of the magnetic path, which is equal to 2 pi into Ri plus Re by 2. This I will employ for determining the magnetic field intensity and also for determining the inductance. So we use it to have this equation, right? L is equal to mu n square I by L. So instead of this L, I'll write it as 2 pi Rm. This is the length of the magnetic path. This is the expression for determining the inductance of a toroid. Now, let us suppose a toroid has two uniformly distributed windings. See, I think I have missed the figure, but I'll draw the figure here. Now let us suppose this is a toroid, and it is having this is one coil, and let us suppose it is having one more coil, which is being wound in this fashion. Now there are two coils now, which is P, the other one is S. Now let us suppose S is having N2 turns, whereas P is having N1 turns. Now one is called as a primary winding, the other one is called as a secondary winding. I'll name these things as primary and also the secondary winding, as we have discussed during the case of mutual inductance. Now for ease of understanding, I'll separate these two magnetic circuits in this fashion. Now, this is primary winding, this is secondary winding, and it is having N1 turns and is having N2 turns. Now let us suppose I1 is the current which is flowing in the primary winding. So you know that the magnetic field is equal to mu H, which is equal to mu N1 I1 by the magnetic field path. the length of the magnetic path, right? Now, this is the B, magnetic flux density. So, how many linkages will be there on the primary side and on the secondary side? It depends upon number of turns and the flux density, right? So, the flux linkages on the primary side will be equal to the number of turns on the primary side into the flux which is being developed. The flux developed is common, right? The flux will be developed in this space. How much flux is linked with this one? It depends upon the number of turns. If you use only one turn, only a small portion of the flux will be linked. If you use large number of turns, then you have maximum number of flux linked with that winding. So flux linkage depends upon number of turns into flux. So number of turns on primary side is N1 into phi. Phi is being created by B, which in turn depends upon N1, right? So the flux linkage of primary winding is equal to N1 into B into A, where B is this equation. So I'll get, this is the expression. Whereas flux linkage for the secondary winding is N2 into phi. Phi is equal to BA. B is again dependent of mu N1 I1 by, yeah, so I think N1 I1 by magnetic. So BA, I'll get flux is nothing but BA, and phi 2 1 is equal to N2 into BA. N2 B is this one, mu N1 I1 by Lm into A is area cross section. So we'll get mu N1 into I1 A by Lm. This is the expression for mutual inductance. See what is the difference between these two. In phi 1 1 you have got mu N1 square I1 A by Lm, whereas phi 1 2 you have got mu N1 into I1 A by L, isn't it? So this is the equation for self-inductance, and this is the equation for mutual inductance of second coil with respect to the first one. Okay. So how to determine the EMFs then? So EMF in the primary coil is equal to minus L11, the self-inductance, due to the change in itself. Whereas V2, which is the secondary coil, the inductance will be mutual inductance, and the current is because of the primary coil. See, try to remember this. Okay, so this is the way how we determine EMFs with respect to self and mutual inductances. Okay, I hope that now you are able to determine the self inductance of a toroid and also mutual inductance of a toroid. Now, see here, when a toroidal coil of 1000 turns has a mean radius of 20 centimeters and a radius of winding 2 centimeters, what is the average self inductance with air core, with iron core, and also what is the EMF developed at t is equal to 5 seconds with air core if it allows a current of 100 sin 22. Now, if you carefully see, it is a toroidal coil. We know for a toroidal coil, average self-inductance is given by mu n square A by 2 pi Rf, right? Mu depends upon the medium, n is the number of turns, A is nothing but area of cross section. You have been given radius of the winding, right? So this will help you in determine pi r square, which is area, 2 pi Rf. This is the mean radius. This is 20 centimeters. So before doing the problem, convert all centimeters into meters and then start doing the problem. Okay. Mu for air core, it is mu naught only, whereas here mu r is 800. Once you determine the L, the problem is solved. Next, what is the EMF developed at t is equal to 5 seconds? Air core, if it allows a current of 100 sin 20t, which means he is asking EMF. You might have got an L di by dt. You have got I So differentiate it with respect to t, and then you substitute t is equal to 5 seconds. You will get the problem. So we will do some more similar problems in the class, but come prepared this video tutorial. Okay, thank you.